So anyways, this is sort of like a goal-oriented talk, like maybe the universe is goal-oriented. So I try to get to this last point through the slides. So basically, is there some sort of teleological principle required in Albrows hypothesis? I don't know if Albrows hypothesis had been formalized, but basically, the way I understand it, it's sort of some sort of principle that there are no infinities. At least, so I'm going to only consider certain types of infinities. So in particular, there's no singularities in the overall history of the universe, and probably in the microscopic history of the universe, at least in terms of geometry. And space and time are both finite in extent. So this could be...
I agree.
This could be some sort of super selection principle on paths of space-time, or it could be inherent in the laws of physics. So I'm going to talk about just a little bit about that. So I want to distinguish it from Hawking's no-boundary proposal. Now, I don't know if you're familiar. So we live in a universe with 3 spatial dimensions and 1 time dimension. And Einstein and others realized you can sort of formalize this mathematically in terms of a metric on a manifold. So it's sort of Riemann's idea, but extended a little bit to allow for time-like dimensions. So basically, we have 1 time and 3 space, but that could change. I mean, it could be that at some point it's all space. And so Hawking's no-boundary proposal, the geometry of space-time looks something like this. I mean, this is a 2-dimensional representation of it. But basically, maybe the bottom of this sphere is the beginning of time, the top of the sphere is the end of time. Now, normally that wouldn't be allowed. That would be some sort of singularity if that were time. But if it's all space, that's fine. In 2D, it's fine to have a purely spatial manifold like this. And if you allow the signature of the metric, i.e. the number, if you allow the time dimensions to go from 1 to 0 at some point in the universe, then you could have a universe like this, where you have we live here, time backward, the past time is here and forward time is here, but at some point sort of time disappears. And in a quantum theory of gravity or of geometry, that's possible. So for the purposes of this talk, I'm going to say that's not allowed. The metric would be singular. The determinant of the metric would be singular at some point. So maybe that's also forbidden by Albrows hypothesis. I don't know. So, but let's just assume that's true. And then you get this sort of cartoon picture of what the geometry of space-time is, at least in a 2 + 1 dimensional form. So basically, there's time, say it goes in this direction. There's space that sort of goes in that direction. And if you go around, you come back to yourself. And you could embed this in a larger manifold where time was periodic. Like things happened over and over again, exactly the same. But that's not the way we want to think about it. As Mike was pointing out, we want to think about it. It's really just one manifold. Things just come back to itself. In time, there's always a time dimension that goes this way. That's not to say that the thermodynamic arrow of time or the experiential arrow of time is always the same. But there is a time, in terms of a Riemannian manifold, there is a time-like dimension that goes around like that. So why is this such an extreme proposal? Well, normally in compact cosmologies begin with singularities and end with singularities, or at least that's the normal solutions of Einstein's equations. So in normal physics, this really isn't what you expect from Einstein's equations with normal matter. So to be more specific, if we go back to this picture, you can cut a slice through here. It's a slice of constant time, if you like. And that acts as both the initial condition and a final condition for all the fields in the universe. So this spatial hypersurface that cuts things in half is the initial and final boundary condition on all the matter and geometry fields. And so what we require for this hypothesis to be true is that the matter, or the configuration of matter, and the configuration of the geometry sort of evolve in such a way so it matches onto itself as it goes around to this final initial surface. And so that doesn't sound bad. But generally speaking, if you take the normal laws of physics, or the least action point of view of physics, that really overspecifies the fields. There will not be, in general, be solutions of that form with any given period. And that's true for classical or quantum dynamics. And I'll go through that in just a few slides. And furthermore, another thing is that temporal periodicity precludes that there is a universal thermodynamic arrow of time. So, I mean, something, if the entropy increases, then the final state isn't the same as the initial state if there's a well-defined entropy of the universe. So let's do something really simple. Consider a periodic universe in sort of a Newtonian point of view. So basically, there's a fixed space and there's a fixed time. If you like, it's a torus, like I've drawn, or it might be some other topology, like Klein bottle or something. It has a period t, and so in the Newtonian picture, space and time are fixed. In this case, they're sort of they're fixed to some odd topology, but they're still fixed. And so basically, you have time times a spatial, well, I shouldn't say R3, I should say T3 for the spatial dimensions, or S3. Now, suppose one had two oscillators, sort of, say, two atoms or something with the oscillator given period, and they don't interact with each other. So they'll have two periods, T1 and T2. And so in this universe, if the universe had two atoms, they would have to evolve their trajectory would have to go into each other. And if they had a specific period, and if the ratio of the periods was was irrational, then there is no period which would allow them to do that. It's just impossible. So this is just an example of how periodicity is not consistent with our normal formulations of the laws of physics.
So that was almost my question about this one-correct theory. I'm still not sure that I understand. Let's say we have just two dimensions, okay, like horizontal and vertical, like in this room. So we're not talking about floor and the ceiling. And let's say I have only one particle, and I just send it with a straight line. So as you said, as soon as it will hit this wall, it will appear on this side, right? And it will continue this motion. And if the angle you have on this plane is not rational, I mean, if the ratio of increment, like velocity in x and y, then I don't even understand how you can have a periodic time in this system, because this particle will cover our whole plane. I mean, if we're talking about the cross-section, it will cover all plane with its own trajectory. It will appear and disappear.
So there'd have to be an infinite number of particles.
Just one. We have just one particle.
No. But I mean, maybe I'll get to that later.
And I mean, I'm not sure how you can now close the time. It's such a
because there's something which I call super periodicity, which I'll get to.
Okay.
But
without knowing where I was going, I take from this that you cannot have such oscillators all the way around the whole loop, and the Big Bang, Big Crunch destroys the oscillators.
I mean, in my understanding.
Okay, I don't want to. Let's hear what
let's go on a little bit further. Right. So anyways, it seems like it's really hard to do this with a Newtonian sort of view of a periodic universe, for this reason. And this is just sort of, this is two non-interacting oscillators that could oscillate, that could interact, and they wouldn't have an exact period, and it wouldn't be so simple. But generally speaking, this just sort of illustrates the fact that the initial conditions are not the type you need to solve a Newtonian set of equations. All right, so special relativistic periodicity. So this is a little bit different. So in special relativity, there's this time dilation effect whereby in a given rest frame, say the universal rest frames, something with in its own rest frame had a given period, and the universal rest frame might have a different period. In fact, the periods are multiplied by these Lorentz factors gamma, which depend on the speed. So if you quantize the velocity, suppose you have two oscillators with two periods which are irrational, you can always pick the speed so that the ratio of the period in the universal frame is a rational number, and it's periodic with any given period you specify. So you can have periodic oscillations in special relativity that you wouldn't have in a Newtonian framework.
But then it's some type of local periodicity. If you have two different sets of oscillators, with gamma 1, gamma 2 will be different.
Well, no, but the two oscillators can move at different speeds. But the speeds are not arbitrary. They have to have specific values for it to work. And furthermore, not only must the time part be period, but the spatial part has to be periodic as well. So that's a more complicated problem I haven't. So I don't know even if you just had two given periods, T1 and T2, allow the Lorentz factors, and allow a torus with an arbitrary size, can you get the spatial parts to match up? I'm not sure that that's true. But it gives you more freedom. So as I'm going to tell you, the history of physics allows you more and more freedom to do things that you would normally think you could do from the previous thing. But there's also super periodic trajectories. So we believe that like all particles of a given type are identical. And in quantum mechanics, you say the wave function of them is completely symmetric or completely antisymmetric, whether they're bosons or fermions. So basically, it's not necessary for a given particle's trajectory to match on to its own trajectory. So a given electron doesn't have to match on to that same electron trajectory at this temporal boundary condition. It could match onto a different electron with the same velocity. And so in that sense, if you follow that electron along the trajectory, the actual period that it would have to have could be any integer multiple times t. I don't know. Actually, I don't have that here. So the period is n times t for any n. And that would be fine. So so you can have super periodic trajectories. So Mike Albrow could go sort of transform into anyone else in the audience as he ages. You could match on to the baby Alex or something. So something like that could happen. So anyway, so we have to allow for that as well. What about quantum periodicity? So in quantum mechanics, particles don't have any particular trajectory. They just have a probability for every possible trajectory. So certainly, even in normal quantum mechanics, there's a probability that the particle will have a given, that the trajectory will have a given period. And if you had some sort of super, or in Feynman's terminology, a given path, so you could just add some sort of super selection rule where you only pick out the periodic paths. And that would be a modification of physics. It would give you different physical laws, but it would allow for periodic trajectories. And so that would allow you to have a periodic universe. But this is, I should stress again, this is not consistent with normal quantum mechanics, since if you take Schrodinger's equation, this final and initial condition thing still over-specifies the equations. There are in general no solutions that are periodic with any given period. But there are, you can have periodic solutions in special cases. We need special laws of physics, which is sort of exemplified by this, the interactions of the particles have to be just right to allow for periodic solutions. So that's quantum periodicity. Well, we can go even one step further, and it sort of resolves all the issues, which is quantum gravitational periodicity. So what does that mean? Well, we believe that everything in the universe is quantized, including gravity, meaning including the geometry of space and time. And that means that the geometry of space and time is not any given fixed value. It doesn't have any given fixed trajectory. But there's a probability over all different trajectories, so all different histories of space and time. So how would this manifest itself? Well, one way of just talking about it is something that, at least in the context of a mini superspace, which is sort of a simplified version of quantum geometry, there's a wave function of the universe. So that would include many, the wave function of all possible histories of the universe, and in particular would include the wave function over the period of the universe, t. So t, so we would live in a universe where all different times were allowed, and for some periods, maybe certain types of oscillators would have greater amplitudes because they're more resonant with that period. And it could sort of resolve all these problems with the fact that, in general, you've overspecified things. So people have sort of formalized this in something called the Wheeler-DeWitt equation. And it's more like an elliptical equation on the entire history of space and time that is a hyperbolic equation that allows for initial conditions. And if you restrict your topology to have a certain form, like a torus, you can do that and solve the Wheeler-DeWitt equation. At least you can solve it for a very simple set of fields. You can't solve it in general with an infinite number of modes, but you can solve it under simplified assumptions. You would have, if you like, a periodic universe. Now the problem with that, and maybe Mike could address this question, is that in general the wave function of the universe would extend to t equals infinity. I.e., t equals infinity would not be forbidden. It would just have a given probability. And in general, it might be that large t's were actually preferred in some sort of uncontrolled way. So that, I think, would violate the spirit of Albrows hypothesis. But maybe you could modify the interactions of the fields, i.e. the gravitational interactions of the matter, to make this t equals infinity part of the wave function suppressed, or add an additional term or something to the equations. So does that violate Albrows hypothesis? I'm not sure, but I think you can sort of, as you've worked your way from Newtonian physics to quantum gravity, you find that periodic universes are, if you like, more allowed or easier to accommodate.
So how many dimensions does the wave function universe have? Does it have like 10 to the 80 dimensions or something like that?
No, this is the wave function of the universe is an idea that was developed by Hawking and Hartle, and it's just 4 + 1 dimensions. It's usually actually 4 + 1 dimension where the number of parameters that describe the evolution of the wave function is like 1, because that's the only case you can solve it in. But
with the number of variables, I mean, we have, let's say, 10 to the 80 particles.
Well, no, in general, it would have 10. It would have an infinite number of. It would have,
very large number.
You Fourier analyze the metric, and there's an infinite number of modes, and there's all sorts of ultraviolet problems, etc. But maybe you can deal with those if you're clever enough. But it's generally believed that there's some sort of, if you like, if you can regulate the ultraviolet stuff, there's some sort of infrared dominance. So to find the wave function of the universe, you just have to solve for the overall scale factor, and you get a good approximation where you can integrate the high frequency modes out in the normal way. Okay, so that's sort of the history of physics, getting closer and closer to allowing Albrows hypothesis. But there's another worrying thing, which is the at least to me, the thermodynamic arrow of time. So we apparently live in a universe where the entropy is increasing with time. And let me skip to the next slide. Here's a picture of if you went into interstellar space and you measured the spectrum of photons, you would see a spectrum that looks something like this. This is electromagnetic radiation. This is the cosmic microwave background. So all of these photons here come from, if you like, the Big Bang, or from very early times in the universe. But all these other photons, in particular the cosmic infrared background, the cosmic UV, ultraviolet, background are added to the universe. So if the universe is finite, then if at a given time, say today, pick some spatial hypersurface, there's only a finite number of photons in the universe. We know what the density of photons is, and if the universe is finite extent, we can just multiply times its volume if it's roughly uniform, and we can figure out the total number of photons. Now these additional bits here are additional photons that add more entropy to the universe. And so if you went to the big crunch, if you like, the total entropy of the universe would be bigger. There'll be more particles in it, even though, deuterium, is dissolving, whatever. That, in a real thermodynamic sense, just counting up the number of modes and how much they're occupied, there are just more particles around, and there's more entropy around. So that's just not consistent.
I'm not sure. I mean, in a contracting universe, what was now the cosmic microwave background is becoming now bluer and bluer, and stars are absorbing photons.
No, stars don't absorb photons.
Well, they will do if the universe is.
No, they won't.
I mean,
stars
they're
stars
sitting in
will
a bath of photons that is getting hotter and hotter as the universe contracts.
Well, stars will evaporate eventually.
Well,
they'll get hotter as this background gets compressed. The microwave background will be 3 degrees. It'll be 10 million degrees.
Yeah.
It will basically evaporate the stars, except for the black holes. Yeah. Even the neutron stars would eventually be dissolved in this stuff. But still, there'll be more entropy.
But
and here we have it's only a few percent increase, but it would still be a few percent increase.
So you don't have a stage of where entropy is decreasing. Entropy is always increasing.
In a contracted universe, entropy is always increasing.
Always increasing.
Always
so you do not have option to match matching conditions.
I haven't
so
understood this
problem.
I haven't understood why in a contracting universe entropy continues to increase.
Well, because what about the second law of thermodynamics is not true if the universe is contracting.
States.
What?
But at the very end of the universe, you will have only a few number of possible states.
Right? No. The number of states will be infinite, unless there's some sort of even though it's a small volume, there's still an infinite number of modes, just as infinite as it is now. If there's some sort of ultraviolet cutoff, it's some sort of Planck physics thing that sort of absorbs states and it probably violates unitarity, then yeah, sure, you can. In that state, you cannot have increase of entropy.
So something should be modified
Yes.
in your picture to make it in agreement with my picture, right? Still, there is a sort
Right, there could be.
entropy. For entropy,
There's an
a disagreement.
exceptional period where the normal laws of physics is violated during the big crunch bang whatever thing. Physics may not evolve as we normally think about it.
How is it possible at all that the entropy would decrease? So as we discussed before, number of states should decrease. Is it possible? Do you see any possibility for that number of states to decrease? Then entropy would decrease in number of states.
Sure. You just stick in some sort of Planck size cutoff to states, and things that sort of get compressed below that just sort of combine into two states go into one or something. You can do that. It's not consistent with our normal picture of quantum field theory, but that doesn't mean it's not true. Doesn't mean it's not true.
Yeah, because the way I think, suppose you had a universe with just electrons and photons, nothing else. Forget about everything else. Just electrons and photons.
Right.
So and when it's hot and small, the electrons are radiating photons like mad. So you get more and more photons, the same number of electrons.
Right.
And then it expands and it comes down. And all the time it's expanding more and more photons, bigger entropy. And as it comes down, it continues, except when it gets to be very small, like the size of an orange or something like that, the photons are actually being absorbed by the electrons. And you get fewer and fewer photons. And when it comes down...
Well, no, but see, if you calculate the number of photons per electron,
yeah,
it would be bigger.
Well, it's time dependent. And
it always increases.
Always.
Always.
even when the universe comes down to be this Fermi or something in size.
Well, I
I
mean,
can't
there's,
get
there's
to any
other
further.
interactions.
I
You're not
can't
going to
get-
just have photons and electrons.
I can't have UV photons in a universe the size of a Fermi, of course. They can't be there.
No, they're super horizon modes to everything.
Super horizon. That sounds like going outside my closed world. Someplace.
I know, it's just bigger than the time for the universe to contract by a factor of 2. Any electromagnetic wave that's bigger than that are just sort of frozen in, and that you have to count those too.
All right, carry on. I have to think about it.
All right. So, anyways, so we apparently, I'm claiming we apparently live in a universe where the entropy is increasing with time, and we expect it to always increase with time, at least with normal laws of physics. And the production of starlight is probably the biggest contributor to the electromagnetic entropy and other big. There's the neutrino background, which you don't see. That presumably has a lot of entropy as well, producing a lot of those in supernova. So a periodic universe would seemingly have to have periods where the entropy, is decreasing. I got that wrong. So it could be that, it could be that is during some sort of exceptional period, like a phase transition, where the normal laws of physics don't apply and people like us don't exist.
Just singularity in a sense, right?
Well, so it's sort of like a singular. It's sort of violating, I think, the spirit of Albrows hypothesis to have exceptional periods in which things are very different.
Well, there's an expensive
Well, so-
time, which is a big
Well, there's the
matter.
ekperiodic, universe, which is claimed actually not to be. I mean, it's not periodic the way you're talking about, but it has a big bang, big crunch, but it's not singular.
Yeah, but I would say
And so that's an exceptional period. And so, but I'm supposing, well, can we have a universe where there is no really exceptional period? So, where maybe experiential time also
by
reverses.
experience you mean the same as psychological time. I mean, it requires the existence of conscious beings to have experiential time, right?
Yes,
That's right.
right. So it's what you call psychological time.
Yeah, which I'm supposing that when entropy decreases in my picture, there's no.
But that's sort of like cheating, if you ask me. You always it's way off in the future when there's no life, and then we don't have to worry about all these inconsistencies because there's no one to tell it. That's really cheating. If you
I
ask
don't
me.
think so. It's not if this big crunch in the crunch when entropy decreases happens in the last, when the universe is now the size of an orange. Of course, there can't be any life in the universe that small.
Well, no, but it's sort of pushing all of the problems to something which is exceptional. So I think that violates the spirit of what I'd like. So, anyways, because you want to talk about philosophy, metaphysics, which really is just according to Aristotle, it's the chapter that came after the physics chapter in metaphysics. So what comes after science? It's sort of science fiction. So the question for me is, can you make a good screenplay out of this new physics?
Yeah.
That's the most important consideration. So could a man who remembers the past mean a man who remembers the future? That would be an interesting thing. Could in the future there be some sort of transitional period that's not exceptional? Okay, so teleology. So now I've got to my last point. So the whole point so far is that it seems like some sort of new laws of physics are required to, even in the quantum gravity case, to allow the periodic universe to really exist. So there's this idea of teleology, which is sort of not first causes, but last causes, the study of the purpose of natural occurrences. And of course, in normal scientific philosophy, there is no purpose. Things just happen the way they happen, and it's not a goal-oriented universe. But here, you can compare two different laws of physics. You can compare the periodic laws of physics. If we came up with some laws of physics that allow for a periodic universe, and compare them to laws of physics which don't allow for it. And you can compare the two.
Do not you confuse, Albert, the solution of equations backward and purpose? Purpose, I think, is a feature of consciousness. So if you are saying about purpose, then I think you immediately implying consciousness. But you are not obliged to do this. If you are saying that I know future situation, I'm solving my equation backward in time, then you do not need consciousness, at least direct.
Well, no, I'm saying that could there be, well, so I've argued that you need new laws. Let me just go. And it seems like if you have, except in the case where you have exceptional periods where the laws are violated, if the laws of physics just allowed them during non-exceptional periods, then these new laws would require improbable events, improbable meaning improbable, according to the old non-periodic laws, events to occur. So basically, for entry to decrease, you'd expect, the toothpaste to go back into the toothpaste tube or something like that,
I keep trying that, it never seems to work.
Well, maybe in some future period. So the thermodynamic argument suggests that we had transitioned from between two regimes where the area of time, the thermodynamic area of time changes or flips direction, if you like. And it could be that during this transition, improbable events will occur with increasing frequency. So that would make a good screenplay.
What does it mean improbable then? If they increase improbable event have a high probability.
No, improbable according to the old laws of physics, but probable according to the new laws of physics. So can you have these two sets of laws coexisting, where you get to test it, where entropy starts, decreasing, and say, wow, entropy is decreasing.
Your cup of tea starts to jump.
Exactly. Albrow was right after.
Do you write screenplays, actually? It sounds as if you do.
All right, or will it be sort of an exceptional event where so those I think are two possibilities. There are probably other intermediate possibilities as well. And so according to this unbeliever's point of view, the Albrows hypothesis would be a teleological principle where the universe appears to act goal-oriented in order to get back to the predetermined final initial state. So, anyways, so I'm phrasing this in scientific terms. We can test this by seeing whether improbable, if normally improbable events start to happen, and it would look, like there's a predetermined final state that the universe is heading towards by will of its own.
Those are my questions.
So I don't know if I have any answers to this.
We may postpone them to the next meeting because I think there are a lot to discuss here.
Right. I mean, I think that no infinities means no zeros, and of course, lots of things. Any continuous thing that goes from positive to negative goes through zero. So it's hard to avoid some sort of infinities.
But your point two here, you're talking about mathematical structures, right? And
Right.
I've
Yes,
always
yes.
said, plenty of infinities in mathematics, and
I understand your
just-
point, but
yeah.
the question I think still there, because in mathematical Platonic world we have infinite number of structures, but still some finite number of structures are employed in our universe, or even if you have super periodicity, still you have finite number of at least laws of nature employed in the world. And then the question is, what or who segregated the mathematical structures to employ one of them in the physical world and disregard or set aside only into Platonic world all the infinite number of other mathematical structures? What is the reason or ground or power? Or what segregated mathematical structures on these two very unequal groups? I think this is a very philosophical, very important question,
Right.
I would say.
But at least if you go to sort of a quantum gravity point of view, what you have is the wave function of the universe where all possible histories constrained by your given topology occur with some probability. It's probably, the way we think about physics, it's not true that all possible physical laws are happening.
Physical laws are still there, so I think that both of you discussing essentially the same physical laws, like quantum gravity or whatever. So all the fundamental laws of physics are the same, just initial condition of specific configurations of the system is changing, but laws of nature are atemporal and fixed for both of you, right? But
Right.
my question is sort of meta question. I'm looking on this fixed laws of nature, and I'm looking on them as a specific mathematical structures, and I'm asking the question, why? It's actually Wheeler's question. Why these specific mathematical structures are employed in our physical world, not something else? What or who segregated all the mathematical structures on two unequal groups? One of them, the smaller group, very specific, very beautiful, is employed, and on other stuff, mostly garbage, is set aside. What or who made this
Well, I
segregation?
So let's put it next time discussion. But could you just
Yes.
go back one slide before we go on to this one? Because there's right. Will it be more of an exceptional event? I'm saying that there is an exceptional event, which is a Big Crunch, Big Bang. And if you were to zoom in on this event and like just look at the universe for the trillionth of a second before and trillionth of a second after, then it looks totally symmetric. That is, it looks like universe, anti-universe pair creation. The Feynman lines, world lines are coming in and going out, just like in a particle pair creation. And CPT applies, and at the minimum, the universe is in a single state with entropy 0. And because it looks exactly the same before and just after, so it has to be the same. So there has to be a collapse of entropy, but on a bigger scale, it's not symmetric because the anti-universe is. Because of. I take the definition of entropy to be the log of the number of final states available to the system, and at the very beginning, the number of final states is 1, and then it's a small number on both before and after.
But that necessarily violates unitarity.
Does it?
Well, there's only one state the universe could be in. It's not consistent with the wave function of all possible states available today. Because there has to be unitary mapping of all possible states now to all possible states during your exceptional event.
Oh, I'm not quite understanding it. I have to.
Can you repeat this statement?
I mean, unitarity says that the space of states evolve in a unitary fashion in order to conserve probability. So if we consider all the possible states here, there has to be unitary transformation into the state during this exceptional event. And there's only one state that's not possible. The dimensionality has to be the same or both infinite, if you like.
Somehow, number of states starts to increase at the beginning, and then number of states is collapsed at the end. So this would normally not happen, right? So,
Right.
but still somehow it should happen in this closed loop universe.
I'm not sure. Like, let's say in a systems with a very strong dissipation, right? You can have a very complicated structure and very complicated dynamics in some intermediate regimes. But finally, everything will fall to the single final state.
Reverse the situation. But microscopically, the number of states hasn't changed. It's just, if you like, all of it's gone into a thermal state, which just expresses our ignorance of what it is. There's all these thermal motions. But in general, it should be reversible.
But in an inflationary picture, which I'm not saying is relevant for this, but at a time after 10 doublings or something like that,
Right.
what is the entropy of the universe?
It's very large.
Very large.
It's the same. It's bigger than when it started.
When it started, it's
suppose you take some intermediate 10 times after.
Yeah.
If it expands by a factor of 10, the entropy is actually bigger, if you like, because there's been all this quantum production of gravitons in that factor of 10, and that adds to the entropy of the universe. Now, the universe has gotten much bigger, so the entropy in a horizon size might be smaller, but you have to consider the entropy of the entire universe, which is very, very big.
How is the entropy of the universe during inflation defined? Actually, it's a number of states available. There's numbers of different states, but I thought it was a single state.
Well, if you like, you can, if you have say, non-interacting particles, it's just basically n log n, where n is the occupation number of any given state. So the occupation number of these graviton states gets populated by quantum graviton production, and it increases.